good. And every so often you can still get very strange results using machine translation. Now, the next topic I wanted to talk about is advances in game playing. And let me start with chess. In 1996, IBM challenged Garry Kasparov, who was then the reigning world chess champion, to compete against a computer called Deep Blue. And Kasparov beat that machine, which showed that chess playing computers weren't quite at human level. Then in 1997, IBM came back with a much bigger computer, and this time Kasparov lost. So I'm going to try and show you a video. If you can see the screen, I already said this is a poor quality video because this is from some archive, but it's kind of fun to watch anyway if the website will load, okay?
Traditional key methods may appear to clean your home, but Dyson research in India.
This was suspense beyond anything the world of chess had ever known. Garry Kasparov, 34 years old, a cheerful and confident player throughout a dominating career, hovered over his pieces in the deciding game of a match with an implacable challenger. Deep Blue, a computer. Kasparov won the first game in a breeze, but the next day he got the shock of his life. To Kasparov, Deep Blue played the second game much more strongly, differently. Unlike a computer, he said. Kasparov conceded, and the loss wore on his mind for the rest of the match. In each of the next three games, the world's preeminent chess players, man and machine, battled each other to a draw. Kasparov's early scorn for Deep Blue's abilities had proven a great mistake. In the final game, the computer led with the white pieces, and soon Kasparov's fans had to admit that the once unthinkable might actually be happening.
Sir, a small correction here. I see that your video is not being played. It's because you're sharing only the Acrobat Reader screen, Adobe screen, the presentation
Okay,
screen.
I'm going to stop the video here because it's not particularly interesting.
Okay, we will share the video to them. We'll share the presentation link to them, so maybe they can understand the video.
You can share the entire presentation because the video link is embedded into the PDF, so they can watch it if they feel like. Okay.
Fantastic, sir. Sure. I'll do that.
I mean,
we can go ahead for now.
Yes. This is yours to do what you want with. So now I want to ask this question.
Surely.
If you heard in the video, D1 Kasparov, Deep Blue 2 beat Kasparov. So, is this an advance in AI or was it just an advance in computation? Well, I say that it's not an advance in AI because the heuristics used by Deep Blue are exactly the same as the heuristics used by Deep Blue 1, except it had twice as many computers. So it wasn't a very big thing. But recently there have been significant advances, things like AlphaZero and so forth. But I'll come back to that a little bit later in the talk. Now I'll show you one more video. This is IBM's Watson. It's called playing a game called Jeopardy, which is like a general knowledge quiz show where the contestants are asked questions, and then they push the button. Whoever pushes the button first gets to answer the question. So I'll show one more video. I hope you don't get another advertisement.
Sagar sir, if possible, try to share your entire screen. That's more easy.
I'm trying to share the entire screen. Okay, I understand. Oh, I'm not. Okay, I understand. Let me go back. Now, now where do I share? Where is the thing that says applications?
Entire screen, sir. Entire screen.
Well, let me.
Your screen.
All it says is the only option I seem to have is stop sharing. Okay, let me try once more. Okay.
Okay, sir.
I'm a bit scared to. No, wait a minute. Okay, applications. Oh, let me see if I can share the whole screen.
Exactly,
Entire
sir.
screen.
Exactly.
Okay.
Yes, exactly.
Okay.
You have to
Well, when the
click on the
video
screen
comes,
again. Yeah,
right,
you
but
will
it
have to click on the
doesn't
screen
allow
again.
me. No, it doesn't seem to allow me to do that. It will not allow me to do applications.
Hello.
Okay, fine. I will share the I'll share the YouTube application. That will be fine.
It's a kind request to everyone not to unmute yourself. This webinar is being recorded. If you have questions, we would always share the recording to you all. We have seen a huge participation and it's creating a little chaos for the webinar. I would request not to unmute yourself unless asked for. Please guys, because if we found it, we'll have to expel you from the webinar. Yeah, we're going ahead with the presentation, but please give us a little time because we're trying to fix the issues. Saga sir, all yours.
Okay, so let me get back to this video. Let me see. It should allow me to show the application window, YouTube, but it's not. So I see someone called Akanksha Singh on my screen. I don't see myself any longer. Yeah, it looks like this whole business of sharing is not working. I mean, the sharing of the PDF is going fine, but the sharing of the okay, well, never mind that. I can see the PDF is sharing fine, but it looks like the embedded links don't work very well. That's okay. You can download the PDF from wherever IEEE headquarters will put it, and
I will send it across to all of them on email. We will be sending it across to all of them on the email, so that shouldn't be a problem at all.
Fine. All right. So anyway, I was just saying that this IBM's Watson, it was playing this game called Jeopardy, and it did beat the human champions, and it was combining speech recognition, search, and speech generation. So because the host asks a question the same way that it asks a human being, so the Watson computer program had to understand the question just like a human. Then it had to search through its knowledge base to find the answer to the question. And then it has to answer again in a human voice because it was competing exactly like a human being. And it won with no handicap against the best champions. Okay. Now, there are two very common board games, and there have been a lot of advance in playing board games in the last 5 years or so. There is a company in London called DeepMind. It's a spin-off from Imperial College in the UK. And it was acquired by Google in, I think, 2012 or something like that. Anyway, they built a computer program called AlphaGo. Go is a board game. It's a 19 by 19 board game. So there are 361 squares. And then the white player has 181 chips. A black player has 180 chips. And the idea is to capture some territory, and whichever player captures the most territory wins. So in 2015, this program called AlphaGo, developed in DeepMind, it could defeat a player called Lee Sedol, who was an international player, but not the top ranked player. And then in 2017, it actually, yes. Yeah, it actually did beat KG, who was the top-ranked Go player in the world. Then DeepMind went forward and started to play chess and Go and
Oh,
Shogi.
mic on हो गया है. Sorry to disturb you, sir. I'm really sorry. Guys, this is the final intimation and final warning that is found if somebody is trying to interrupt the webinar by unmuting themselves. They're expelled from the webinar with no action with requisition. So this is the final chance. If you are having a trouble, don't worry. We're already streaming live on Facebook. We're already recording this video on the WebEx platform. We'll be sharing everything in detail. If you find it difficult, we would request you to get back to our Facebook page where you can see this webinar live on Facebook rather than creating a disturbance here, because we have put a lot of efforts into this. So please cooperate with us. This is the final chance, guys, please. Yes, sir, please. Saga, sir, please.
So the interesting point about this computer program called AlphaZero, one can say, what is the difference between AlphaZero and AlphaGo? The difference is the zero refers to the fact that it doesn't have any prior information. So whether it was the Deep Blue programs that played Garry Kasparov 20 years ago, or AlphaGo about 7-8 years ago, they both used human expertise as a starting point. But AlphaZero basically didn't start with anything. It just played against itself and got better and better. So that's what I meant in this last bullet, saying it doesn't use prior knowledge. Now, interesting thing is that the AI community for 50 years had believed that prior knowledge helps you to do better. So in other words, if you're given a choice between learning from scratch and taking advantage of prior knowledge, you should actually use prior knowledge. But the fact that AlphaZero eventually seems to outperform the programs that use the prior knowledge turns the whole AI business kind of on its head. So the research community is still trying to understand whether this is just a one-off phenomenon or there is a fundamental reason why using prior knowledge is actually a handicap and not a benefit as people thought. So in this slide, what I'm trying to say is what's behind the current successes. So in decreasing order of importance, I would say the availability of massive amounts of training data, advances in computation, and special purpose hardware such as GPUs and Google sensor processing units. And the third bullet is advances in algorithms in machine learning. Now you may say this is a bit funny that I have put advances in algorithms at the bottom as the least important advance, and I have put availability of massive amounts of data as the most important advance. And this is quite deliberate because earlier we had very clever algorithms, even 15, 20 years ago we had them. We had neither the amount of training data needed to make these algorithms work properly, nor did we have the advances in computational to run the size of problems that we required. Now, the third point I wanted to, the last point I wanted to make on this slide is AI is now democratized. What I mean by that is there's a lot of open source software available. So if you want to write your own AI application, you don't really need to be extremely knowledgeable. You can just download all this open source software and you can start going. Now, of course, the downside of democratization is that you can also misuse the software in the sense that people will download some software just because it's free. They don't bother about what kind of a problems it is meant to solve. They don't bother about when this algorithm will actually work properly. Then they complain afterwards that they're getting bad results. So that's the downside. But the flip side, the good side is that anybody can now build pretty good AI applications. So what are the potential trouble spots for AI? Well, first thing is that many of the very impressive looking results, especially in image processing, are pretty fragile. So in other words, when people try to reproduce the results that are claimed in the publication, they don't get them. Or even if they do get the original results, if they make slight changes in the image base, they get massive degradation in performance. Normally, we expect that if it is a good algorithm and is working well, we change the input data slightly, it should still perform more or less the same. But this doesn't seem to be the case, especially in the domain of image processing. Also, as I mentioned, many results are not reproducible. People will publish a paper saying, I ran this algorithm and I got this. And you say, okay, let me also run the same code on the same database, and you don't get that. So what do you do then? The other thing, the next set of bullets here, the last 4 bullets, have to do with the commercial aspects of AI. So IBM's Watson winning this game called Jeopardy was, of course, a great achievement. But then they tried to sell it as a commercial product, and especially they tried to sell it to the medical community for personalized medicine. That means instead of just giving the same medical treatment to everybody, Watson was supposed to enable the doctors to fine-tune the treatment for each individual. And what spoiled the prospects of Watson was that it sometimes gave incorrect advice. So this made the doctors very, very reluctant to use Watson, because obviously bad advice is worse than no advice, right? And then Google, once it created this AlphaGo and AlphaZero, they said, okay, now we have this universal problem solver. You give us enough money, the code is yours. Well, the point is nobody has thus far been able to make it into a universal problem solver. So it looks like there's a lot of hand-holding required to make it work for any specific application. So the bottom line very simply is that neither the Watson nor AlphaGo has been a commercial success. Okay, so the point is very impressive technological achievements, but not much in the way of commercial success. There are a few other problems as well. The current claimed successes in AI are all based on using massive computational resources. So for example, the AlphaZero, which is a program that is supposed to learn chess starting from nothing, if I remember correctly, it uses something like 1920 GPUs. Now you imagine how much resource that is. Probably in typical university, there might not be 2000 GPUs in all the university put together. So the idea is that when you use this kind of a massive computational resources, other than a few enormous companies, probably nobody can do actual computational research in AI. Especially when you go to a field called deep learning, this is becoming increasingly true. And the third bullet here is that the mathematical foundations of deep learning are not very well understood. In other words, if you don't have good mathematics, in some application works, it works. If it doesn't work, you don't know why. And even if it does work, you're not sure that it's going to work the next time. Okay. On the other hand, the traditional neural network learning, which you may call shallow learning, they're pretty well understood. So there is this big gap between the level of understanding of neural network learning as soon as you go from more traditional learning to deep learning. So the main challenge now is to develop a suitable theory to explain why deep learning works at the scale at which it is practiced today. Now, I won't try to play this video, but there is a lecture from Dr. Ali Rahimi of Google, who received what is called a Long-Term Impact Award from a meeting called NIPS. NIPS is Neural Information Processing Systems. It's one of the most prestigious events in this area. So they gave every year an award for a paper that has stood the test of time. So Dr. Rahimi and Dr. Rex wrote a paper in 2008, and in the year 2018, pardon me, it was judged to have been the best paper written 10 years earlier. And the interesting point about this video, if you watch it, is that Dr. Rahimi slams a lot of current research and learning as alchemy. He says it's basically rubbish, it's not reproducible, and this is not how we should be doing research. So obviously it didn't make him very popular with a certain group of people, but those people who like theory were all agreeing with him. So that's about all I wanted to say about the historical background of AI. Okay. Now let me talk about the evolution. How did we get to where we are? So let me point out to all the young people sitting here listening that this is not the first time there was a lot of hype about AI. This is actually the fourth cycle. So in 1950s, there was something called the Perceptron, invented by a man called Frank Rosenblatt. I'm not quite sure about the level of hype because even I was just a little boy then. So that's why I said third or fourth cycle, because I'm not sure of the first one. But the second, third, and fourth were all very, very real, and they were all great hypes. So in the 70s and 80s, there was something called rule-based expert systems. In 80s and 90s, artificial neural networks, and currently reinforcement learning and deep learning. So rule-based expert systems have kind of vanished. Artificial neural networks are still with us, and in fact, they have reincarnated themselves as deep learning and reinforcement learning. So what can we learn from past failures as well as successes? My view is that technologies that have a solid mathematical foundation have survived, but others have not. So let's go back to the early days of AI. So this slide, as you can see, had a lot of links. Unfortunately, doesn't look like I can play the link. The first bullet was about Alan Turing proposing something called the Turing machine. It is a universal model of computation. There's nothing much in the link. It's just a photo of Turing, so you can find it on Google Images if you want. The modern digital computer started in 1946. And John von Neumann proposed what he called the reprogrammable computer, which has since been called von Neumann architecture in his honor in 1945. And Norbert Wiener wrote a book called Cybernetics in 1948. And then Alan Turing proposed what he called the Turing test of machine intelligence. So the idea here is, when do you call a machine intelligent? So Turing said, well, if you go into a room and there's a curtain, and behind the curtain is either a human or a machine, and you can't tell which is which, then obviously it's an intelligent machine. That's what he said. And interestingly, Claude Shannon, who is very well known for having invented information theory, he wrote a paper about how you can actually program a chess-playing computer. And this paper is way ahead of time because the kind of resources that were available in 1950 were extremely primitive. In fact, computers didn't even have transistors, they used vacuum tubes. But Shannon, being a visionary that he was, he foresaw how you can program a computer to play chess. This phrase, artificial intelligence, was coined by a Stanford professor called John McCarthy in 1955. So the point I'm trying to make is many of these ideas are quite old, and if you see this particular slide, some of the all-time great thinkers are all on this slide: Turing, von Neumann, Wiener, Shannon, McCarthy. So because this field was shaped by so many very bright people, it continues to be very alive even today. So here's a photo of Turing, and here's a photo of the ENIAC installation at Princeton. That is not von Neumann, it is just somebody working there. So what I'm trying to mention in this slide is that the aims of AI have evolved over the years. Okay. Initially, when AI started, the research community was very, very focused on reproducing how humans do things. So in other words, if you want to program a computer to do vision, you try to understand how the humans do vision, and then you replicate in a computer. Same thing with language processing. Artificial neural networks came by trying to figure out what are the neurons in the brain, how do they get wired, and then build a network that looks like that. And the deep blue architecture that I mentioned in the beginning, which took on Garry Kasparov, was actually built by interviewing a human grandmaster. That is, the IBM people asked the human grandmaster, how do you play chess? And then, to their surprise, they discovered that human grandmasters, in fact, don't analyze millions and millions of positions. They just analyze not more than 10 or 15 possible moves. So they try to build that into the computer program. So I call this thing operational AI. So operational AI means you are trying to replicate human functionality at a very fine operational detail. Now, what has happened in the last 20 years or so is that the research community has moved away from this. They don't pay any attention to reproducing human functionality. Instead, they say, can it do what a human being does? So, for example, can my computer program interpret images? Doesn't matter if it does the same way as a human or not. Can it understand languages? It doesn't matter if it does the same way or not. Can we build a neural network where the neural characteristic is not at all like what is in the human brain? And similarly, this deep blue architecture has been replaced by this alpha zero architecture, which doesn't have anything to do with how humans play chess. So basically, what I'm trying to say in this slide is AI research has undergone a complete metamorphosis whereby the objectives went from replicating human operational details to just matching human performance, never mind how the computer does it. So I just have a few slides on building machines that can reason. The reason why I'm going to not spend a lot of time on this is that the bulk of the talk is going to be on machines that can learn and generalize. You can faintly see that as the next topic, building machines that can learn and generalize. But it will be kind of unfair not to mention building machines that can reason. So I just have a few slides on that. So very early in its history, AI has bifurcated into two branches. Hello? Okay. So very early in its history, AI bifurcated into two main branches. One is reasoning, and the other is learning and generalization, and the methodologies were quite different. So reasoning was exemplified rule-based expert systems, and learning and generalization was exemplified by neural networks. And the underlying mathematics is very, very different. And the point is that most of the current excitement is from learning and generalization, not on rule-based reasoning systems. And within this current excitement, there are two hot areas, deep learning and reinforcement learning. Now, just to look ahead a little bit, you will see that I'll say very, very little about reinforcement learning. The reason being that the mathematical barrier to understanding what reinforcement learning is pretty high. So I just have one or two slides explaining what it is about, but no details. In contrast, for deep learning, I will actually go through quite a bit of detail. So let's get back to this rule-based expert system. So what the rule-based expert system, which started in the 1970s, tried to do was to figure out how do human beings reason and then get a computer to replicate those thought processes. So there were people called knowledge engineers. Sorry, there's a typo there. but you can figure that out. There were people called knowledge engineers who interviewed human experts and then distilled their knowledge in the form of a series of rules. Okay. So here's a toy example. If it rains, then I will open my umbrella. Of course, nobody will actually interview to find out this rule, but what they would do is, let's say a person is operating a chemical factory. The knowledge engineer would say, what do you do if this particular alarm comes on? And then the human expert would say, well, if that alarm comes on, then I do this. So they capture this in the form of a set of rules. So you can see that when you interview human experts in order to derive knowledge, whatever computer program you have cannot outperform the experts because they were the source of your information to begin with. On the other hand, the reason why these expert systems were very popular was that they greatly accelerated the learning curve. So if you had a novice, let's say a novice operating a chemical plant, that person could reach the level of expertise of an expert very, very quickly. So, and they were pretty good for that, but they had fairly severe limitations in the sense that they could not handle rules that were not very, very cut and dried. And that's why I didn't put a whole lot of material. And also, as I said, current excitement is not about that. Current excitement is about machines that can learn and generalize. So, in reasoning, the output of the computer program is a truth value. Rather, you say, well, something is true or it's not true. There's an intermediate possibility. You say, well, I think this is true with a certain confidence factor. So what I mean by confidence factor, suppose a person goes to a doctor, and let's say that instead of a doctor, you have an expert system. The expert system can look at the symptoms and say, you have dengue fever. Or it can say, well, I'm 90% sure that you have dengue fever. So there's a slight difference between declaring some statement to be true and then declaring it to be true with some confidence factor. This is what reasoning systems used to do. But now, we don't get so excited about reasoning systems, we get more excited by learning systems. So within learning system, there are two broad classes, and you need to understand this difference. If the output of program is a binary number, 0 or 1, or +1 and -1, this is called a classification system. Okay? And if the output is a real number, between 0 and 1, or between -infinity to infinity, this is called regression. Now, classification networks and regression networks are somewhat different, not hugely different, but the type of applications are completely different. So you could think about a reasoning system as a classification system. So for example, you can ask a learning system, does this patient have this particular disease? And it is supposed to say yes or no. That is the case of a binary classifier. On the other hand, suppose there is a cancer patient and the cancer patient has undergone surgery and the surgeon wants to say, okay, when should I schedule the follow-up checkup? How long will it be before the tumor may come back? And you have to make a prediction. You say, well, 586 days. So you don't have to see this patient before 586 days. So that number is a real number. So that is an example of a regression learning system. Whether it is a binary classifier or a real number regressor, the philosophy is the same. You have what is called training data, and all of this training data is what is known as labeled. That means that with each training data, you either have the classification if it is a classifying network, or you have an associated real number if it is a regression network. So once you have trained your network, you give it some previously unseen data. So the person who is assessing the neural network, that person knows the answer, but the neural network is not told the answer. So the previously unseen data is fed into the neural network. It makes some prediction, and then the correct label is unmasked, and then you compare how good the prediction is. So if it is a classification problem, which means that you have to say 0 or 1, you see what fraction of the time you get the right answer. And if it is a real number, you can't just get the right answer or wrong answer. You also have to figure out if you have the wrong answer, by how much did you miss. So missing by a little bit is not so serious. Missing by a lot is quite a bit more serious. So you do what is known as the least squares error. That means you take the difference between the actual value and the predicted value and add it up over all the test data. There's one more thing which is called supervised versus unsupervised learning. So in unsupervised learning, you just have data. There is no label at all. So in the world of statistics, this is called clustering. So you're just given a bunch of inputs and you want to put them in groups. And each group has the centroid, which is the average of all the vectors in that group. And when you want to choose the centroids in such a way that every point is closer to the centroid of its own group than to the centroid of any other group. Illustration on next slide. I'll just do this and come back to this slide. So suppose you have this data. Now, one of the weaknesses of clustering is that you have to specify the number of clusters beforehand. Okay? And there's a very popular algorithm called k-means. Now, suppose you were to say, I want to group my data into 3 clusters. Then you would get cluster number 1, cluster number 2, and cluster number 3. But now suppose I say, no, I'm happy to have 5 clusters. Then what will happen? Nothing much happens with this or with this, but then cluster number 3 gets divided into 3 subclusters, as you can see. In general, this is a very difficult problem, and you cannot solve it exactly, but this k-means is a very widely used heuristic. So now what happens if you have a new input? What you do is, you have to assign it to one of the clusters depending on to which centroid it is closest. So if I get a new input here, it's closest to this cluster centroid, so I say, okay, it must be in this group. If I get a new input here, it's closest to this centroid. If I get a new input here, it's closest to that centroid. What happens if I get a new input here? Right here. Can you see? The distance between my new test input to this cluster and this cluster is pretty much the same. So there are a couple of things you can do. You can say, well, I will assign it to this cluster with some confidence and to this cluster with some other confidence, which is not very good. The other point is you say, well, this is an outlier, so I'm just going to ignore it. So these are kind of the common ways in which you can do clustering. This is called unsupervised learning. So now let's get back to supervised learning, building machines that can learn and generalize. So let's start with the early neural networks. The very first neuron was something called the Perceptron. It was a device with just 2 outputs invented by a man called Frank Rosenblatt. So what it did was, it took a bunch of real inputs and then it would put out either a -1 or a +1. What it would do is to take a weighted sum of all these inputs compared against a threshold, and if the weighted sum was more than the threshold, it put out +1. If this was less than the threshold, it put out a -1. Now, I read in the internet that somebody called Arthur Samuels built a perceptron that could play checkers, but I must confess very honestly, I haven't been able to find any details of Mr. Samuels or his perceptron that could play checkers. So there is something called training a perceptron. So you have a bunch of vectors and the associated labels, and the idea is to choose a vector W, the weight vector, and the threshold theta, so that you correctly classify this training inputs. And if this weight and threshold exists, this is said to be a linearly separable data set. So here's a picture. Look at all these green dots. Suppose that all these green dots are given the label of +1. And all these maroon dots are given a label of -1. So you can pick any one of these straight lines that I've shown in dotted lines, and they will all correctly classify the data. On the other hand, if I change this maroon dot to green, or if I change this green dot to maroon, you can see there is no way to separate the green dots from the maroon dots. I hope people can see that. So in this situation, what you can see is either there is no straight line that separates the two classes, or there are infinitely many straight lines. So when in this situation where there are infinitely many possible ways to discriminate between the green dots and the maroon dot, which one is the best? This leads to a notion called support vector machine. A support vector machine is one where the closest point is as far as possible. So this line here is the support vector machine. I'm just mentioning it because people might have heard of a support vector machine but don't quite know what it is. Of course, for illustrative purposes, I have just chosen two-dimensional data. In real life, you would never use this kind of a machine learning with such low-dimensional data. You would use far higher dimensions. Now, here is a picture, and here I did exactly what I mentioned in the previous slide. I've changed this dot, which used to be maroon, to green, and I've changed that dot, which used to be green, to maroon. Now you can see there's no straight line that will separate the maroon dots from the green dots. So you say, well, all right, I'll just find a straight line that misclassifies the fewest number of points. That problem sounds very nice, but you can't solve it because it turns out that this is an NP-hard problem. So what you have to do is to find efficient approximations to solve this problem, or you can go for a nonlinear classifier. See, this function that we had earlier, this is called a linear classifier because the output is just sign of this function, which is called the discriminant. But you can use a nonlinear function instead of this, and this leads to something known as kernel-based classifier. So here is a picture. So if these are the points labeled -1, these are the points labeled +1. There is no straight line that will separate the two classes. But I can have a more complicated separating surface, and this is called a nonlinear discriminant function. Let me go back to this picture. If I insist on correctly separating all the maroon dots from all the green dots, I'll get a completely crazy surface which looks like this. So you have one of two choices. Either you say, no, I don't want to, I want to separate all the maroon dots from all the green dots. Or you say, well, look, obviously that is an outlier which has been mislabeled. Obviously there is an outlier that has been mislabeled. And I'm going to use a much simpler classifier. So typically people use the second approach. If some very small number of points is not fitting the data, you just simply disregard them. The key, of course, is the word small. You can't disregard too many points in this approach. All right. Now, there is a very famous counterexample from 1969. This is called Exclusiveor. So what this says is, suppose you have two Boolean variables, x and y. And we define the exclusive OR to be true if only one of them is true. So if x is false and y is true, the exclusive OR is true. If x is true and y is false, again the exclusive OR is true. But if both are false or both are true, the exclusive OR is not true. Now you can see at a glance that there is no straight line that will separate the two green dots and the two maroon dots. So it's not a big deal, but for whatever reason, people lost faith in perceptrons after this. So for about 17 years, nothing happened. Then suddenly in 1986, there was a paper called Multilayer Perceptron Network, that revived the subject. It was by Rumelhart, Hinton, and Williams. And then they rediscovered an algorithm from the circuit theory literature, and they called it backpropagation. And then years later, this was in '86, in the early '90s, people showed that the neural networks had what is called the universal approximation property. And there was also very rich theory. Why do multi-layer perceptron networks work? So, for example, I wrote a book in 2003 called Learning and Generalization. It's full of equations. I don't recommend you to read it unless you really want to know the subject at a very, very high level. The point of this bullet is simply to say we know pretty well why multilayer perceptrons work. Just to look ahead, we still don't know why deep learning works. So here is an example of a multilayer perceptron network. So there is an output layer, there is an input layer, and then there are the so-called hidden layers. And typically, the networks of that day had just a few, 2, 3 hidden layers. And during the early days, people wanted to model the human brain by using this artificial neural network. So they were called ANN. Now, the brain neuron kind of looks like this. It quiescent for a long time, then it goes up very steeply and goes down again. So people use this as a neuron characteristic. But as time went on, people dropped. The reason why these were called artificial neural networks was because people wanted to mimic the functioning of the human brain. As time went on, people realized that we are not trying to mimic the human brain, we just want to solve problems. So now we just call neural networks. Then people said, all right, if we just want to reproduce the abilities of the human brain, why does the neuron have to look like this, which is the brain neuron? Why can't it look like this, for example, which is called the rectified linear unit? So it turns out, people said, yeah, we don't need to stick to this one because we're not trying to mimic the human brain anymore. We just want to do anything that works. So this particular thing called the rectified linear unit is far more popular now than the sigmoid. Okay. The problem with the sigmoid is that, as you can see here and here, the gradient, the derivative of this function is very close to 0. I will explain many slides later why this is a problem. So it's important when you do neural network training to just 1 minute. It's very important when you're doing neural networks to make a distinction between training and testing. So you train a neural network by adjusting the weights. That is all these numbers in here. There are weights of all these edges. You adjust them till on the labeled input data, the output more or less matches what it wants to. That's the training phase. But that's not important. What is important is that if you show it some previously unseen testing data, you should get the right answer. So when you have a neural network that has far too little data and far too many parameters, you get a phenomenon known as overfitting. So you get very good performance on the training data, but very bad performance on previously unseen data. This is a phenomenon that actually predates neural networks. It goes back to statistics. More than 100 years, people have known this. But recently, what people have done is, so you can see let me go back. Can you see 3 faint outline here? Deep learning neural network, recurrent neural network, long short-term memory.
Yes, we can, sir. Yeah, we can.
So I'm just going to talk about each of these fairly briefly. So
sure.
In deep learning, what happens is that the neural networks have just a few layers and maybe a few thousand parameters. So you could train them comfortably with maybe 100,000, a million inputs. But now, the neural nets of today have hundreds of layers, millions, even hundreds of millions of adjustable parameters. So, unless the amount of training data is in the many, many high millions, possibly billions or even trillions, these kinds of networks can suffer from overfitting. So what happens in the deep networks is there are lots of heuristics to reduce the complexity of training and to avoid overfitting. Now, let me get back to something I've said several times in this presentation, which is we don't really understand why deep learning works. So people are using heuristics. Well, they may have one or two or three examples where they work nicely, but that doesn't mean that it will always work. And that's one of the things we need to understand going forward. There have been some good successes of image classification of deep learning. For example, image classification, the ImageNet challenge is a challenge, is a success story of deep learning. Sorry, I garbled that sentence. Let me try again. Deep learning has had a very major success story in the ImageNet challenge, where the task was to classify various images. So that obviously that period shouldn't be there. Okay. Now, I have one slide on current research in deep learning. So you may say, okay, I mean, DeepMind people have come out with AlphaZero, AlphaGo, so what is there left for me to do? Do I just download the software and start running applications? No, there's still plenty of stuff to do. For example, deep learning requires the minimization of non-convex functions of millions of variables. If you don't know what non-convex means, look it up later. But basically, convex optimization is easy. Non-convex optimization is very, very troublesome. So people have evolved some new methods. For example, there is something called stochastic gradient descent, which sort of seems to work, but we still don't fully understand why it works or even when it will work. And standard statistics, as I mentioned, for over 100 years, people have known that if you have too many adjustable parameters and too little data, you get an overfitting, which means you get very good performance on the training data and very bad performance on testing data. But deep neural networks don't seem to suffer from that, and we don't understand why. And you can't understand why through simulations. You can only understand why by doing a mathematical analysis. So this is a very hot area of research right now. Now let me talk about recurrent neural networks. This is probably the most difficult part of the talk, so try to pay attention. So all the neural networks we have seen thus far are called feed-forward neural networks, or FFNN. This multilayer perceptron network are an example of FFNN. Essentially, these kinds of networks don't have any memory. So there's some nonlinear function f, the function of the weight and the input. And once you have chosen the weight through training process, for example, when you assign an input, it produces an output according to this function. But now suppose we put in a sequence of inputs, not just one input x, but x of 0, x of 1, x of 2. You put it into this feed-forward network, then what the network does is it ignores the time dependence. It just simply applies the same function to each of these inputs without regard to the previous history. That's what I mean by saying the feed-forward networks have no memory. But you do need memory if you want to get good results. So I just put two sentences here. Can you read that? Would you like to have coffee? What kind of wood is in the furniture? So just say this to yourselves and just listen to yourself and ask yourself, do I pronounce that word wood differently from the way I pronounce this word, wood? I think the answer is no. You probably pronounce both of them exactly the same. But when I say this, would you like some coffee, on the telephone, for example, you know that it is WOULD and not WOOD. How do you know that? It's because of the context. So if you have a speech recognition system and you put in wood, it probably won't do particularly good job of distinguishing between this one and that one. But if you put in the sentence, the speech recognition system will do quite a good job because it has a context. But now the question is, how do you build context into a neural network? So recurrent neural networks are basically a way of feeding back past input in order to improve the performance. So a speech recognition neural network, which is a recurrent network, would be able to distinguish between that sentence and this sentence. So how does it work? The traditional feedforward network just pushes data in one direction. See? Start here, go there, start here, go there, start here and go there. That's it. There is no feedback. But in a recurrent network, so there is a summing junction and there is a neural nonlinearity. This produces, so you have all these inputs multiplied by some weights, and it goes into the summing junction, and this quantity z of t goes to a fixed nonlinearity. See, there is no t in f because f is the same at every time, but the input is varying with time, so it produces an output at time t. But then what you do is you take this output, put in a one-step delay, that's what delta is, one-step delay, and you feed this back with its own weight so that you can improve the performance. So this is the most basic building unit of a recurrent neural network. Now you can have more complicated feedback structures. As you can see, there is one feedback here, I could put more here, as many as you feel like. So you can go down multiple levels of feedback, and there can be multiple such feedback, and there is an analog of backpropagation known as BPTT, backpropagation through time. I won't bore you with the details, but it works pretty well. Now, there is something called a long short-term memory neural network, and this is a very important advance because all these machine translation programs use long short-term memory. So what is it? So we had this method called backpropagation through time, which I didn't tell you about fully what it is. But basically what it does is it uses the least squares cost function and the gradient of that to adjust the weights and to train the network. So if this is your least squares error, you have to take the partial derivative with respect to each weight. And in backpropagation through time, each of these partial derivatives is a product of a whole bunch of individual partial derivatives. And if any one of them is small, the overall gradient is small. So suppose that one of the neurons are saturated, it is either here or there. Then it doesn't matter what is before or what is after, the overall gradient will be 0, which means that your network doesn't adapt anymore. So that's bad. So this is what I said here, the gradient is indeed small if the input is large. So what people do is, to get rid of this problem, they change this sigma to something like the recursive, the rectified linear unit that I mentioned earlier. So here is a general recurrent neural network. We have a whole bunch of input and a whole bunch of output, but then each of them is fed through its own delay and fed back. Okay. Now this is only a one-step delay. What happens if I have multiple time steps? Then it can get very complicated. And if you kind of unroll this network, that means you remove all this feedback and make it into into a feed-forward network only. Then what happens is that there are way too many connections. So this little one single feedback recurrent network is unrolled into a whole bunch of feed-forward neural networks. Now, because there are so many parameters, it's kind of difficult to train this network. So the so-called LSTM, long short-term memory, was evolved to cope with this situation. So there are various approaches. I don't want you to try and read the slide in real time because you will get you can download the PDF from somewhere. But essentially, there are these units, and then you just keep using these units over and over again. And the key point about sorry, I didn't come to this. The key point about LSTM is that it has something called the forget gate. So what is a forget gate? It basically means if you have all these previous inputs, you ignore some of these inputs from the distant past, saying that they are not particularly important. Now, this phrase, long short-term memory, is a bit bizarre, right? So what does it mean exactly? It means the total number of time steps that you go back is quite long. That's why the memory is long memory. But you only use a few of these past inputs. That's why it's short term. And this forget gate is meant to say that once you have used up that short term memory, it gets flushed out of the system and it is not used anymore. So because of that, it works quite a bit better than a standard recurrent neural network. So I'm finishing exactly at 12, which makes me very happy. This is my last slide. I mean, essentially my last slide. I said that reinforcement learning is a very hot topic, and I've told you nothing about it. So why is that? It's because the topic is very mathematically advanced. The entry barrier is quite high. However, I would say at this point in time, it's a hotter topic than deep learning. The reason is that people don't fully understand why it works. Now, the reason why the entry barrier is so high is that reinforcement learning builds on a topic called Markov decision processes. And so you look them up. There are some decent introductions, but they're all fairly advanced. So in a Markov decision process, you have a present state, you have to take an action, then you get a reward, and you have to figure out what is the optimal policy, and you have to solve what is called a dynamic programming problem. This is a reasonably well understood model. But the difference between a Markov decision process and reinforcement learning is that in Markov decision process, the underlying model is known, and reinforcement learning, it has to be inferred. I know this slide is very, very vague and abstract. The reason is because I can't, in a limited amount of time, tell you what a Markov decision process is. But I do want to tell you one thing, that programs like AlphaZero are success stories of reinforcement learning. So just let me summarize. AlphaZero is a success story of reinforcement learning. Okay. Machine translation is a success of long short-term memory. And image recognition is a success of deep neural networks. So each of these hot areas has had its own success story. In the case of reinforcement learning, there's a lot more research to be done. Even though AlphaZero seems to work, it is not very clear whether it will always work. And more to the point, can you always achieve AlphaZero-like performance with far fewer resources? So this is really my last slide. I'm going to spend a few minutes describing this. The reason why there's a lot of excitement in machine learning now is because the recent approaches, recent successes, sorry, this word is wrong. This is not approaches. These recent successes in machine learning have involved genuinely new approaches and new algorithms. Okay, that's why there is excitement. Understanding why, how, and when these new algorithms work is very essential to ensure continuing success. And the research focus has shifted slightly. Maybe 7-8 years ago, people were just running lots of simulation. Now people are not so persuaded by just simulation. They want to say, look, why does this work? You say you ran it 10 times and it worked. Well, maybe you're just hiding the 100 times that it didn't work. So I don't believe you. So this was not true 5-10 years ago, but it is true now. So now there are a lot of people tuning in. Presumably you want to be an AI ML engineer. I would suggest to you that you avoid the bag of tricks approach. What I mean by the bag of tricks approach is, as I said, a lot of software is out there. You just download it, you put some wrapper around it, and you say, I am also an AI engineer. Then you're a bag of tricks engineer. You won't be very successful. But if you learn some fundamentals, then you will be quite successful. So that's my talk. So if you want, you can open up the floor to questions. Probably you can put your questions in the chat and Vamsi can ask the questions on your behalf.
Yep, I'll do that. Because if considering the fact that we have close to 200 people already on the platform, it would be really tough if you open the floor for them to shoot up questions. However, maybe I'll pick few questions. Probably, can we get the recorded version? Yes, we will definitely share the recorded version to all of you. Okay, I'll go up. Okay. So yeah, the floor is open for the questions, guys. I mean, if you have questions, maybe this is the time you have to push them into the chat box, the chat window which is there. I'm trying to scroll through all the questions that are there here, and okay, I see. Okay, so here is the first question. Okay, this is personally to me. Where is it? The audio is all about. Guys, this is the time we have questions. Okay, so this question is from Vineet Podar. Where to begin the understanding of AI and ML, artificial intelligence and machine learning? Like, where do we actually start it with?
Yeah, well, I think it depends on what you mean by understand AI. I always make a distinction. Do you want to know what it is about, or do you want to know what it is? So if you want to know what it is about, a kind of a general talk like mine, there are lots of such resources on the internet. So that will get you started to know what AI is about. But if you want to know what it is, there aren't that many good books out there. There are some books by people like Chris Bishop on machine learning. You just have to look at the internet. But there are books that tell you what AI machine learning is about, and there are books that actually try to teach you machine learning. So you've got to figure out what it is you want to know. It's not a very cogent answer, but I don't understand the question.
That's great. And I see this question coming. I guess some of the questions are like that can be Googled out. I really don't want to take some time in asking them. Yeah, this question seems to be like critical to me as well. Like, can any of the algorithm implemented in quantum cellular automations?
I'm sorry, any of the algorithms?
Implemented in quantum cellular automata.
No, not really, because you see the kind of problems that are addressed by quantum computing are very, very different. Okay, so the kind of problems that quantum computing tries to solve, for example, in coding, entanglement and disentanglement, key distribution, cryptography, those are the kind of areas in which quantum computing is superior to conventional computing. So it's kind of a different offshoot. I didn't even talk about that. All of these algorithms that I talked about are implemented on conventional computers.
Great. Thank you, sir. So this question is from Ankur Kulkarni. So the role of AI in domains that includes humans and humans to find it hard and computers to find it easy. Like, can we know the reason why you excluded it from your slides?
Can you just repeat the question?
What is the role of AI in the domains that humans find hard and computers find easy?
And that's not AI. If computers find it easy and humans find it hard, it's not AI. That's just routine computation.
Great. Yes. Okay. Maybe this is something that might be interesting. have to become a very good researcher in this field? Like where and what is the best policies, I mean, to be a very good researcher in terms of AI and ML?
So in the case of research, I think the hottest research area is reinforcement learning, because that's the one in which there's a lot of gap in what we understand. Okay, so you should read some books on Markov decision processes. Don't bother about reinforcement learning, just understand Markov decision processes just by themselves, and then start reading some of the recent research papers on reinforcement learning. In terms of deep learning and LSTM, there isn't a whole lot of theory. The challenges there at a research level are, as I mentioned in one of the slides, I hope I can find it again, about non-convex optimization. Yeah, this one here. You have to do minimization of the non-convex functions of millions of variables. So people use the stochastic gradient descent algorithm, but it's not fully understood yet. So there's a lot of work to be done here. So those are kind of the two good areas in which there's lots of scope for doing theoretical research.
Okay, that's great. So, sir, I have this question from a student point of view, because usually we have a very huge set of members of IEEE student members. So everybody tries to understand how to do a research. And I mean, if I ask you, say that, sir, what are the 3 best tips I should follow in publishing a paper, or how should I understand that, where should I start with a topic? I mean, that's a quite. I have seen students in colleges asking that when we say IEEE, okay, so IEEE is all about downloading papers and all, but how do I publish a paper, and what are the best tips I can follow in writing a very good paper? Maybe that is one question that can be asked.
No, I think I would say the following. Most papers that I have seen get rejected because they're not clear. So most people write very badly, and the reason why they write very badly is because they think very badly. So explain your research to fellow students who are not necessarily specialists in your area, but who are also engineers, and that will improve your presentation skills. And then once you understand how to present your ideas in a way that others can digest them easily, then you simply write down the way you have explained it to your audience in a paper. That will greatly improve the likelihood of the paper being accepted. So in other words, I'm saying that if you're an inexperienced author and you straight away start trying to write a paper without understanding what it is you're doing, then the result will be very poor, and the likelihood of your paper getting rejected is quite high. And the second thing I would urge you to do is, okay, you're a student, you read, let's say, 50, 100 papers. Some papers are very easy to understand, some papers are very hard to understand. So you try to analyze and figure out, why is this paper easy to understand and that paper hard to understand. Then you figure out what it is about a paper that makes it easy to understand. Then you try to replicate the same traits in your own writing style. This is how I improved over time.
Okay. Sir, I mean, the webinar discussion when Puneet Mishra, sir, who is the Secretary for India Council, pulled this up. We try to push it as much as we can. So, I mean, if as a student, where I should actually see at AI and ML in future, like how it, I mean, we have been hearing a lot that is been rolling on internet, but as a student, if I have to adopt AI or ML as my career, where do I see it at, and how beneficial it is going to be?
I mean, is the question from a career standpoint, whether is
Yeah,
AI,
from a career.
is a person asking whether AI is going to be a lucrative career in the future? Is that the question?
Yes, sir.
No, I think no. in a subject like electrical engineering, no subject will last 10 years. Okay. So even if you're an AI
Okay.
engineer and you get a job as an AI engineer when you finish your degree, whatever it is, within 5 to 10 years, there will be something else. So you have to be constantly learning something new. But certainly the way things are now, um, AI will definitely provide a solid career for about 10, 15 years. The secret is to keep track of new technological developments. Like this is why we have organizations like IEEE that keep giving us the opportunity to stay on top of new technology development. If you keep doing that, then you will always remain contemporary. But so let me modify the question and say, is AI a good career for the current time? Yeah, absolutely, no question about it. Is it going to be enough for a 40-year working career? Not a chance. You have to keep adapting.
I can understand. Okay, so there is one question we got from our Facebook Live, which says that except Markov decision process, is there any other algorithm that can be used for decision making?
For reinforcement learning, at the moment, that's the way in which people are interpreting it. In other words, reinforcement learning is just a phrase, okay? It doesn't mean anything. You take a right decision, you get a good reward. You can take a wrong decision, you get a bad reward. But those are just words. So if you don't turn the words into a mathematical model, you don't have a theory, right? So right now, the only theory that people have for quantifying these vague phrases like take a good decision, you get a good reward, take a bad decision, you get penalized. The only way people have now of modeling that is Markov decision processes. Now, it doesn't mean that tomorrow someone can come out with a new mathematical model, but for the time being, that seems to be the dominant model.
Great.
And
so,
I should add one more thing.
I can,
I'm sorry, I should add
yes.
one more thing. Markov decision processes with unknown dynamics. That's what reinforcement learning is supposed to be.
Fantastic. So I guess with this, we will keep this webinar to the final conclusion stage. Maybe I'll take one last question, which is web services clustering. This can be found out best technology, algorithm, AI. I guess this makes enough of. Okay. One last question from Saurabh Kulkarni. At what stage is the AI in power systems right now, either in budding or in a growth or a fully developed stage?
I think you're talking specifically about power systems, smart grid type of thing?
Yes, sir.
Oh, yeah, it's pretty advanced actually, because so, for example, there are a number of applications of AI. First of all, there is the load forecasting problem, that is the short-term, medium-term, long-term load forecasting. And then you have to figure out the pricing. That is one aspect. So, see, when you talk about electrical network, there are two very distinct things. One is, roughly speaking, how much resources do you commit to generating power, okay? Second one is, what is the price at which you sell the power? Okay. And in both areas, AI is reasonably prevalent. So this whole there's one Professor Pramod Khargonkar at University of California at Irvine. You can catch that name. You can look him up on Google. Pramod Khargonkar, Khargonkar, University of California at Irvine, Irvine. He has done a lot of work on AI in smart grid.
Okay. So, yep, I guess that makes. Sorry, the questions are done. So, if you have any questions, you should be writing back to me because I'm the one who has written to all of you. So, with this, I guess probably I'll share my screen. Okay, pages. Yep. So I would request everyone here to, I guess my screen is visible right now. So Vijay Sagar sir, really thank you so much on behalf of IEEE India Council and especially from India Council Student Coordination Team. This is our second webinar within a span of 1 month. The previous webinar was on workplace skills, and today we drove a completely purely technical webinar. And this wouldn't have been possible without any of your support. I just wanted to share some numbers. So we started the webinar surveys and we received close to 800 plus registrations, and we tried to restrict as much as we can, but we couldn't stop anybody, and that's the reason we have been playing this webinar on multiple channels like our Facebook page and our YouTube channels. So thank you so much once again from on behalf of IEEE India Council. I am indeed honored to represent India Council to host this webinar for you. So
It's my pleasure.
Great having you here. Great, sir. So I would request everyone on the webinar to take out this link, that is webinar to SIT, which should be helping you to understand that who has attended the webinar. So we have the data of the entire one. So we will try to share this data with you again. So with this, we wrap up and hope to see you all in the next webinar. So the chat window is already there. So we can go ahead and good day. Happy Sunday. Thank you, sir.